EECS 281, lecture number 7, the STL, spring 2020. Today we're going to talk about the STL and how it affects the things we do in class and the ways to look at libraries in general and some good information. Before we get started though, we do have some Project 2 information to report. A good portion of your grade on this project is going to be implementing a pairing heap. So be sure you don't leave this to the last minute. It is a substantial chunk of the grade on this one, about 25-30% of your overall project grade. So it's not something you can just wait till you're done with the simulation and get this done. You should be working back and forth between parts A and B. It's easy to get stuck on one thing. The good news is with two parts, you can always work on the other part. So you've got three different priority queues you need to implement in part B and a simulation for part A. If you get stuck on part A, then you go to part B. If you get stuck on part B, then you go to part A, and so on and so on. Keep yourself working. The last thing you want to do in this tight timeline is get stuck for a period where you're not being productive. Crucial to the pairing heap is your meld function. It's used by just about all of the functions. It's the way that pairing heaps grow and repair themselves. It should be, in the best way to write this, a function that returns a node pointer and accepts two node pointers. Each node pointer, of course, being a pointer to the root of a heap, and then the result being the root of the heap that is a combination of the two heaps that were passed in. You're melding them together. This should happen in constant time. And another thing that you might want to think about here is trying not to do any null pointer checks inside of meld. We'll talk more about that later, but I want you to think about that as you get started. Is there a way to do no null pointer checks inside of meld? Because if there is, then your code is going to be faster. This is an answer from Quora. Great place to spend, or some might say waste, a lot of time. People ask questions there and then they get a group answer and people vote on which answer is the best. So this question is, why do most people on programming sites, why do they use C++ in there as their default language? And the answer is because of the STL. It's got so much high quality code that's written in there that if you master what's in the STL and you start to think of your program being developed in terms of what the STL offers and how you can maximize the usage of the STL, you really can be efficient. And that's what the programming teams do, is they write macros, which isn't great coding style, but it's really good for speedy, quick things that you want to write in a quick one-off for a programming contest. And using macros and using STL is really, really, really productive. So that's why we talk about it. What it is, of course, the STL stands for the standard template library. It's included in C++. It's been, vastly expanded since C++ 11. It's very well documented, high quality implementations of the best algorithms and data structures, and all you have to do is use some namespace stuff and go to work. All of the implementations are entirely in header files, and this is because it's a standard template library. The template means that when it's compiled, it can work with any type. So this is why the STL can't be pre-compiled and just put into a library that your code could link into, because those type informations wouldn't be available at compile time. So everything in the STL is in a header file, which is great. You don't have to worry about linking or any of that stuff. The other very cool thing about that is all the code is available. The STL is 100% readable by you with your downloaded copy of your compiler. So I'll have to admit that it's not the most readable code. It's written in a style that the STL library people use. So there's a lot of type defs because this code is very flexible on what platform it's used on. So there's a lot of, not type defs, sorry. There's a lot of if defs. So you can see if this particular function is available, then use this with a particular container or algorithm or whatever. So you'll see you just have to do it. So the first time you take a look at STL code, it's going to be fairly cryptic. But as you find something that you know how it works, go look at vector pushback. It's a pretty straight, but I can see how pushback works. So you can sort of do that and expand and slowly read more and more STL code. It's pretty important. It's also helpful if you go into the things that we talked about in the algorithm library. There is going to be a question on the midterm exam from the algorithm library. Essentially, you will have to implement one of these functions. And as I mentioned, this won't be the same style as the STL proper. So you aren't expected to make it look like the STL. But having seen the actual code in the STL is going to make you more familiar with what the style is, more familiar with the functionality is, and that's more important. So take a look at it and don't just peek once, because if you peek once, it's not going to be great. You're going to have to look multiple times. If you want to see something about how the deck is implemented, is a pretty crazy piece of code there, but it's all there. Check it out. The contents, of course, we'll talk about it, but Wikipedia is another good resource for getting some information on the background of the STL. There's containers and iterators in there, which of course we've already used and will continue to use more. Memory allocators, which we somewhat sidestep. We don't worry about how memory allocation works in the STL as we use it in 281. We use the default memory allocators. That's something that if you want to customize, the STL has the ability for you to do that. So if you've got some other resource constrained environments, or you've got a particular way that you need memory to be allocated, that's a thing that's available as a flexibility in the STL, just not something we use in 281. There's utilities in there and a strong use of function objects. And of course, there's algorithms, plenty of those in there. STL resources, these are some general resources. The C++ language is not a direct reference on the STL. It's a language reference written by Bjarne Stroustrup, the benevolent dictator for life. Oh, that's Python. Sorry. Bjarne Stroustrup, though, is the author of C++, the book and the language. In this case, amazing computer scientist here. And it's currently in the 5th or maybe even the 6th edition right now. But any one of these things is great. I like books like this because I can get a couple of different uses out of them. I found that good reference material like this, if I sit up and read it, I can learn something. Or if I'm feeling like I want to get some sleep, I can lay down and read it, and right away I'll be asleep. So you have to be careful with these books. They aren't exciting. They are reference materials, and they are somewhat dry. But you can learn a lot from them, and the side benefit is it can help you if you've got some insomnia problems. The second book, this is Jasudis. This one is a standard library reference. So there's some tutorial stuff in there. So it's not purely a reference manual, but it's not a full-on textbook like we're trying to teach you things. It's a textbook more like we need to be able to look some things up. So that's what's there. It says C++ 11 on there. Many things changed between C++ 11 and the prior version. We're at C++ 17 right now. Far fewer things have changed between C++ 17 and C++ 11. So the C++ 11 reference is still very, very applicable in almost all cases. Other places you can do this is cppreference.com and c++.com. They're both different versions of an STL reference site. I am more prone to use c++.com. I'm more happy with the way it's laid out. The information is identical or equivalent at the least to cppreference.com. And the added benefit is cppreference.com actually runs a little faster. c++.com is quite slow. But all the information's there, and usually when I'm looking something up, it's not a race to get to a documentation point. I want to see the thing, think about it, and put it to use. Both of these sites have sort of demonstration code with every function or every member function that goes on in an object. They usually have a small piece of code there, and both of the sites also have a feature where you can interact with the code that's on the site. In CPP reference, it's called Run This Code. In C++, it's called Edit and Run. You click on that, it opens up another browser window that has connection to a compiler, and you can edit code right there in the browser window, compile it, and run it. So this is really great. When I'm trying to figure out how something works, I go look it up and I say, that looks good for your example, but how does that apply to what I'm doing? And rather than having to set up a whole bunch of stuff and try something that I don't know if it's going to work, I can usually in 4 or 5 lines modify the online example to be much more applicable to what I'm doing, to see whether or not this is truly the functionality that I'm looking for. So I use that a ton, and I would strongly suggest getting used to doing that as well. At the bottom, there's another link here to a good tutorial on the STL. That's from Top Coder. You can find some good stuff there. So when we're using libraries, there's always the option of, why don't I just write this code myself? So we'll look at the pros and cons versus using a library and doing it yourself. In 281, we're going to limit your library usage to just the STL. However, I'm sure that if you've done any searching so far already in class, you jump out on Stack Overflow with a question, and most responses are saying, hey, you can do this with the Boost library in just one line. It's great. The Boost library is a lot of fun, but it's not something that's standard, and it's not something that's that we support in 281. So during the course, you're going to have to use the STL. Afterwards, however, you have the ability to go use Boost to your heart's content. So the pros are, some algorithms and data structures are just hard to do. I don't want to have to write a lot of code when I don't need to. I don't want to write difficult code. I don't want to have to write more code that needs to be debugged, or have more places where I'm unsure about whether the error exists in that piece of code or in this piece of code. So that's great. When it's hard to do and someone else has done it for you, that's a good thing. Some of them are easy to sort of write basically, but if you want it to be very efficient, that's hard as well. Libraries make that happen. Another good thing about a library is they are done by committee. They are well planned out, and they have sort of an approach that works for all aspects of the library. So you get this uniformity. So all of the algorithms that do a certain sort of thing are going to be, regardless of what library file they're in, they're all going to have the same types of interface. They're going to use the same ordering of parameters. And so that uniformity makes it really easy, because libraries are vast and they have lots of information in them. And it's always hard to memorize every detail of anything. But when a library is constructed consistently, you don't have to memorize details always. You can often just memorize trends and say, well, I think the parameters should be in this order, and you'll often be very correct with that. So that's a good thing about using a library as opposed to writing it yourself, right? You write a portion of a library yourself, and then a year later you need another portion, and you're thinking slightly differently, and then you put the parameters in a different order, and then you add some more to it 6 months later. And then as you step back a couple years after this has all been put together, and you start looking at it, and you'll see your own inconsistencies because you didn't plan it out ahead of time. And so libraries give us that because they are planned out ahead of time. And the other great thing about using a library is it reduces the debugging time, because for the most part, you can always count on your libraries to have been written by committee and having been well tested and checked. And even when bugs are found, they're usually quite quickly pushed through the community and fixed. And so then you end up with code that's just high quality, and you don't have to debug the code that's in there. And if you work at it and you learn and understand the parts of the STL, you can actually write the majority of your code in the STL, where the majority of the work is being done by the STL code. And that's great, because if your code spends 70% or 80% of its time inside the STL, that means there's only 20% of the actual problem that needs to be debugged at any given time. So that's great, because this will reduce your debugging time, and that's where most of our time as developers is usually spent, is in testing and debugging. So if you can get that cut down, then you're in great shape. The cons are few, but there are some of them, and they're appreciable. So libraries are written for everyone. So they've got general purpose implementations of all of these things. And general purpose works great almost all the time. But in many situations where I've got a specific way that this is going to go, I can cut out some general purpose stuff. So general purpose things make checks that protect everyone, but if you know, for instance, that your data won't have to be checked for this particular aspect of it, then you can cut that out. You end up with something faster. So since these general purpose implementations are usable by everyone, your specific implementation might be a little better. One thing that will come to mind on this is how next permutation in the STL works versus us using genperms in Project 4. And next permutation is a general purpose implementation of a permutation generator. So it will generate all the permutations. That would be great if that's what you wanted. However, we want to use the permutations for branch and bound activity in Project 4. So that means we can look at some portion and say, this is a bad start. And rather than doing the 10 factorial things after this bad start that I know are all going to be bad, I would like to shortcut that and just not generate them. Genperms will do that for you, but because next permutation from the STL is this general purpose version, there's no way to sort of get in the middle of that and say, okay, these are bad, let's not do them. So you lose some flexibility with that general purpose implementation. It's written for everyone. So your specialized code can definitely run faster when you say, I know this is going to go this way, or I know this could never happen. I don't need to make checks for that. So it's very nice. You can skip some unnecessary checks. Interesting things there. So there's trade-offs. I've talked already about needing to understand the library well. You can't use it if you don't know what's there. If you don't know how to use it, it's not going to be any use to you. So you need to look at the data structures. You need to look at the algorithms. You need to understand the complexities of operations. That's what's very nice about the STL is the complexities of operations are a part of the documentation. So it'll say, what's the complexity of pushback on a vector? This is amortized constant. So some of the things that we do as we're learning how to find the complexities of code is great. We don't even have to find the complexity of code on the STL. It tells us it has to be this or better. So that's pretty nice. But as I mentioned, you're not going to know this stuff without finding it. And how do you learn how to use a library? It's just like a regular library, or something that we use probably a little bit more than libraries, grocery stores. You know when you go to a new grocery store and the layout is different. If you've never been to this particular Kroger or this particular Bush's or this particular Meijer or whatever, the layout is going to be different. And as you get used to the store, you come back the second time, the third time, you're like, oh, I don't know where this thing is. I've never bought it here, but I've got the feeling that it's over there because I've been in an aisle that's similar to that. The STL is very much like that as well. So you need to know what the contents of these things are. You need to know the names of the containers. You don't need to know the in-depth details of every single one of them, but having some familiarity with it is going to be great because you can then say, well, I know there was something on a page that looked like this, and you can go back and find it, and you'll end up with something that works out pretty well. So you need to know the complexities of things, and you need to know some of these algorithmic details as well. So you can look up STL sort, for instance. That one's implemented n-log-n worst case. That's great. In practice, it's typically faster than quick sort. It uses quick sort, but if you know the details of these things, then when you go to use them, you're better off. Some examples, nth element. This one is implemented in average case linear time. We can get faster that we know if we've got sorted data, but that's something that's not guaranteed. So nth element is going to work in that average case linear time. These are just examples. They aren't very important things, but they're relative examples here. In the older STL, linked lists didn't store their size, which is kind of strange. It's a small amount of memory and a lot of time savings, but now that memory is being used and the speed has been turned up a little bit. We can get that in constant time. How do you learn all the STL algorithms? Well, you got to read them. That's all there is to it. Read the names of them, read the brief descriptions of them. So when it comes time to do a task, you should be thinking, in all cases, is there a way that I can make the STL do this for me? And this is what takes time, is you have to try to do it. You have to try to use the STL rather than just saying, I don't know how to use it and I can just write this loop myself. Yes, you can, but the STL can probably do that loop for you as well. And in many cases, it's going to be faster than the loop you write. So practice with small programs on the sites, like I talked about, having their ability to edit code right there online, but Write your own tester programs. We're working on being some aspect of a computer scientist if you're in this course, right? And musicians practice music all the time. They don't just go to concerts and perform. Basketball players don't just go to arenas and compete. You have to practice. There's no different here. English majors, they write a lot of papers. They read a lot of books. There's no difference between what anyone else does as a profession and what we're talking about doing here as our profession. If you want to be good at coding, you have to write a lot of code. And I know we're having you write a fair amount of code in 281, but that's not enough. You need to write more. And not only do you need to write more code, you need to read more code. So go on Top Coder, start reading some of these solutions. You can see a problem set from Top Coder and you can try to implement that problem set yourself, or you can also just go look at previously implemented solutions and you can learn something from other people's coding styles. You learn something from other people's usage of the STL, and you can really get some good information by just practicing your craft. So practice a lot with small programs, read and write code every single day. Every single day. I know I'm a little over the top, but that's the way it should be done. There's detailed coverage in the books, obviously. The STL card that's posted on Canvas has a really nice resource someone pulled together. It's just a bunch of one-liners about all of the functions in algorithm, which is great. It's a great place to start. You should scan that once a day until you feel like you can almost memorize the names on a thing. I don't want you to memorize it, but I want you to feel like if someone asks you, can you do this? You would think, oh yeah, there's a sequence modifying operation named blah, and I can go use that. So practice, practice, practice. That's how you learn something, because it's impossible to memorize the whole thing. Well, it's not impossible, but you have to have some pretty serious gifts. And most of us are just normal people. That's good. You don't need to memorize it all. You need to be familiar with what's there. Because if you're familiar with it and you know how to look it up, life is going to be good. All right? So don't try to learn it all by heart. Just skim through it. Every day you should skim through it. If you spent 5 minutes a day just reading different pages on the STL, you would be far better off by the time we get to the final exam here. And far better off as you move through your career. Learn one particular container a week, or pick up utility this week and algorithm next week and numeric the week after that and functional after that. Do something that's just a way that you can sort of skim through the documentation. This is not unlike just kind of walking through the grocery store. Sometimes you go with a list of things you're going to get. Other times you're just like, I know I need food. I'm going to walk up and down the aisles and throw things in the cart till I get enough. So you should be doing that as you're trying to learn this library. Study something that seems interesting. Today I'm going to read this page, and I'm going to skim 15 pages and read one page in depth. So pick some number, get yourself a plan, and then just try to stick to it. And make sure that it's a reasonable plan, because if you try to get too aggressive, you won't do it and it won't work. So maybe your aggressive plan, maybe your plan is, I'm going to skim 4 pages and read 1 page in detail a day. Maybe it's, I'm going to skim 3 pages and read 1 page in detail every other day. Get something that's a reasonable way that you can do this, and then you'll learn a lot and be able to use this STL a lot more effectively. The STL relies on some C++ features. It uses bools quite a bit, often a little bit more than we use in our own code, but that bool thing is pretty good. It uses const correctness and const cast all the time. Const, of course, helps speed things up. When the compiler knows, or the processor knows, that this particular thing is const and not going to be changed, it can speed things up. Of course, there's namespaces, and a lot of times in our 281 code, we just type using namespace standard, dump everything in there and use it, and that's fine in 281. It's not the greatest practice outside of 281 for real professional code, but then you can use a second version of that where, you know, I've included vector and I just want to make sure that I've got standard vector out of there. I can type using standard vector, and that's all I would pull from that library. So you can do that. You definitely, as you're moving forward, you don't want to put a using namespace standard inside of a .h file that someone else might include that they're trying to use your code, because then that forces them to include everything in the namespace, and they might not want to. So don't worry too much about namespaces, but know that they're something that the STL uses. Of course, templates, that's what the T in STL is. It uses templating from C++. You can get some more discussion about templates and how they work from the C++ book by Bjorn Strustrup. Inline functions are used by the STL, stuff that we won't talk a whole lot about, exception handling and implicit initialization. Operator overloading is done in the STL quite a bit, and we've got an extended syntax for new that's used in the STL. And other things that are also used are the two keywords explicit and mutable. So explicit is used to help us, well, we got a slide on that, so we'll go to it, right? Keyword explicit should be used with these one parameter constructors to prevent sort of this accidental conversion. We want to be in our code at all times. We want to be more explicit than implicit. And so there's a nice little feature of conversion, type conversion, that allows some implicit things to happen. And often we're okay doing that. But one of the warnings that you'll get is if you build a constructor that has one parameter, you're going to get a warning that unless you use the explicit keyword on there, right? And so you see this declaration here, given explicit feet inches from int feet. So this is sort of a constructor of feet inches. So this is a one parameter constructor of an object named feet inches. And so you see here, this explicit keyword is used in front of that. And what that does is it says, if I do this sort of thing, so I'm declaring feet inches and I'm giving myself one called feet inches 1, and I'm making this explicitly from the one parameter, 3 here. This is me calling the constructor. Whereas this next one, as I try to assign the integer 3 to feet inches, the compiler is going to say, well, I can't assign 3 to a feet inches because one's an int and the other's a feet inches. But I do see that there's a constructor that goes from an int to a feet inches. So I could use that. That can lead to some problems down the line if you're not careful. Sometimes you don't want to convert a particular way, and the way to prevent those problems is to use explicit. This is why that complaint is there from the compiler. So just drop that explicit keyword in front of your one parameter constructors and you won't get the warnings. A mutable member, that's something that you'd probably be using in this project now. We can use mutable to take a member of a constant, a member of an object that we've got constant reference to and still change it, right? So in the particular application we're talking about the zombies. Zombies hit points. Those are something that should be mutable, because if you stick a zombie into a priority queue and then ask the priority queue, hey, what's the most important zombie right now? You're going to get back a constant reference to it. You cannot change that reference. You see it's the most important zombie and you shoot it once, say, well, now it's got fewer hit points. I want to be able to lower those hit points. If you haven't marked hit points as mutable and you get a constant reference to a zombie that's in a container, you will not be able to modify those hit points, right? But if it's marked as mutable, then you can. So mutable is another functionality that is a C++ way to allow you to shoot yourself in the foot, right? So if you use mutable poorly, you will definitely cause yourself problems. So understanding when things should be mutable and when they shouldn't is something that you have to do before you use it. In this case, the reason why it's okay the reason why the priority queue gives you only a constant reference to the object in there is because the priority queue doesn't want the object to be destroyed. You're not trying to do that. It doesn't want the object to have its priority modified, because if its priority is modified while it's inside the priority queue, then the priority queue can no longer reconstruct itself properly. So if you put something mutable in there, make sure that it's not going to affect priority. And that's pretty straightforward. Hit points don't affect priority. Now, what you wouldn't want to do is make distance or speed a mutable thing and then change those things while you've got an object inside a priority queue. So use mutable. You can see a good example of it in the unordered fast PQ class. There's the unordered PQ that shows how to get the thing done in linear time, and then the unordered fast one Doesn't change the overall linearity of it, but it does speed it up in some instances. So that one uses a mutable member function, and it's a pretty good example. Generic programming. We talked about this in our previous lecture when we were talking about why would I write a for loop like this with dereferencing and plus-plussing when I could just use square brackets, right? The STL uses this generic programming because it minimizes pointers and dynamic memory allocation. When that goes down, our debugging time is dramatically reduced. And the generic programming aspect of it helps me reuse the same algorithm, or the STL really, can use the same algorithm with multiple data structures. So an algorithm that would sort, for instance, standard sort, since it doesn't say sort this vector or sort this deck, we don't need two different versions of it. So if you have a version that only sorts vectors, someone said, well, I would really like to sort this deck. Okay, well, let me write you another version that only sorts decks. The STL doesn't work on the containers, even though it provides them. STL works on ranges, which is what iterators define. Where does data start? Where does data begin? And with an iterator, how do I get to the next piece of data? So then I can use an iterator that I could use the same behavior on a vector, the same behavior on a deck, the same behavior on a linked list, and so on. So that's what the generic programming in STL does. It reuses the same algorithms because instead of making them specific to a container, they're made more generic by using iterators. So it's great. It's much more difficult to do in pure C, but with C++ and the templating that we've got, it actually works pretty well. In terms of performance, the STL is pretty hard to beat. Most STL implementations have the best possible complexities for a particular interface, so that's pretty good. As I mentioned, you still might be able to write your own slightly more effective custom implementation if you know something special about the situation. But even if yours is a little faster in execution time than the STL, it probably will not be a better complexity class, because the STL is going to be using the best possible complexity class for just about anything they can. So sort gives you an n log n no matter what. Some of them have a surprising complexity, like nth element has got this average case linear time. That's pretty interesting. You have to look into how nth element works and try to think about how could you make nth element big O and an average case. Then, as a third thing you could do, you could jump into the nth element code in the STL and look at how it's actually implemented and sort of really bring the whole investigation around full circle. Some of them have poor performance, which is okay. Even with a good implementation, like a linked list doesn't have the greatest performance. It's got its very own narrow use case for the linked list. The main priority, however, in the STL is just going to be time performance. The STL is written to be screaming fast, and it does really, really well. The STL containers we're going to be using in this semester, we looked at vector and deck already. We've done those. We've looked at stack and queue a bit, haven't used them much. We also learned that stack and queue are really just adapters. Stack and queue are adapters that can be placed over deck. Stack can be placed over a vector. Stack and queue can also be placed over list, meaning you can implement a stack with a deck as the underlying container, or a vector as the underlying container, or you can implement a queue with a list as the underlying container. So that's something that's in the declaration spec, so you can look at that to see how you want to change that if you ever needed to. Not something we would do in 281, but something that you can do if you needed to in the future. Bit vectors are the same as a vector of bool. That's something that does some interesting memory savings there. I've got a vector of bools. I can actually save about 7/8 of the memory, right? So if I have just a bool, I'm going to have to put that in a byte. Everything that I deal with has to be at least a byte size. So if you think about what a bool is, it's just a single 1 or a 0. It's a 1 or a 0. It's on or off, true or false. But if I've got two bools, I'm going to keep them in 2 separate variables. It's going to cost me 2 bytes. If I got 10 of them in 10 separate variables, it's going to cost me 10 bytes. If I put them in a vector of bools, that's just an adapter on a bit vector. And a bit vector says, well, if you only want 1 bit, I can stick these in there and pack them tight. So it sticks them in there in groups of 8. So if you declare a vector of bools that's 32 bools long, instead of it being 32 bytes, which is what you would have if you declared 32 of your own separate bools, the bit vector is going to pack those in and say, well, I can put in 8 bools per byte if I'm only trying to stick them in 1 bit at a time. So if I were to declare a vector of bools that had 32 bools in it, it would probably only cost me about 4 bytes data size, because I can look at those values and look at them 1 bit at a time. So that's just something that's not a common use. It's just things to understand about the STL trying to be efficient and effective. There's sets and maps, and they've got multi-set and multi-map versions. We've got unordered set and unordered map versions, and those are talking about the underlying container. We'll talk more about sets and maps in the second half after the midterm. Lists, of course, is the STL doubly linked list, which we'll talk about only pejoratively in 281. The list is a really good container, just not one that we use here in 281. And then there's the array template, which is another one that we don't use too much in 281. It's somewhat limited just because it's got a fixed size at compile time. And one of the reasons why we really like to use the STL is it's given us this flexibility here. So array class from the STL is very similar to C style array in that you have to know at compile time what the size of that container is going to be. So other than that, it's very similar to the vector. So if you have the choice to have to know something at compile time so that you can use an array, or to not worry about whether you know it at compile time and you can use a vector, then a lot of times you just end up using the vector. One more discussion here on linked lists. We won't use them a whole bunch, but understanding what's in the STL is important. The one that's just called list, right? This is a doubly linked list, and it's got a size member in there so that you can ask the thing, what's the size of this container, and it can respond in constant time. The S list is a singly linked list, and the STL doesn't enforce the fact that this can be done in constant time. So it says in the documentation that it can be big O of n. So some implementations might just use next to figure out how many items are there. Another implementation might say, well, I could do it in that time, but I could also spend the memory and keep a member variable around it and get it to you in constant time. But that's up to the implementer of the library. It can be as slow as big O of n, and that's something that you need to know. And then there's a forward list, which is another type of singly linked list. And for some reason, you can't even check the size on a forward list. So just understanding what's in there is important if you need to use these containers. That's why this slide is here. We're saying don't use them in 281. They're probably not going to be helpful in terms of space and speed. As well, the autograder will deduct points if you use S-list, the singly linked list. It includes smart pointers, and that's something that we're not really supporting in 281 at this time either. Copying and sorting arrays. This is just some example slide here to look at how some STL stuff does. So we've included vector, we've included algorithm, and thrown all of their junk in there with using namespace standard. So that's great. We have no worry about finding things. You can see I don't have to put standard : vector or standard : copy or standard : sort. I've just got those things. So what this piece of code does is it declares a vector here of size 100, fills it with a bunch of negative ones, and it also declares me a C-style array of size 100, both of them holding integers. So I'm going to be playing around with those things just a little bit. You see a for loop here, my favorite style here. At the very least, I know this is an n-based loop here. And this for loop goes and just fills the vector v with some randomish looking stuff. It's not really random, but j cubed mod by n is going to look pseudo-random. It's not a good pseudo-random function, but it's an average pseudo-random function. So that's all we're doing there, just to show that you can put some data in there. Lines 12 and 13 are using standard copy. And standard copy has 3 parameters in this usage here. Where the data starts from the source and where the data ends from the source, and where the data should go in the destination. In this case, we're going to be using things that look like iterators. v.begin is an iterator to the beginning of the vector. v.end is an iterator to the end of the vector. And that end is not pointing at good data. Remember, the STL uses the half-open interval where begin is pointing at the first item and end is pointing at the item that we don't include, right? So begin here, end there. That means B is in the data set and E is the location that never really gets included. So it's just before that. So I always say that v.end is always pointing just past good data. If that's the case, then all of the data is somewhere between B and E, or begin and end. So as I copy from V over to R, you say, wait a minute, that's an STL function that, Siri, go away. That's an STL function that is being used on a vector and a C-style array? Yes, we can do that because the C-style array, we know that is really just a pointer. And the thing that the STL generic function copy works with is it says as long as you give me something that looks like an iterator. An iterator can be compared because I need to know if my data is done by saying is begin equal to end if I reach the end. So I need to be able to compare them, I need to be able to increment them, and I need to be able to dereference them. And I can do all of those things with a C-style pointer. I can compare a C-style pointer to another C-style pointer, I can increment a pointer, I can dereference it for read or write. So the generic aspect of the STL allows me to do this copy function from vector to vector, from vector to dec, from dec to list, from list to C-style array, from C-style array to vector, and so on and so on and so on. So that's really pretty cool. See, the next version of it goes from the C-style pointer, this is in line 13, back into the vector. So in these cases, this is pretty powerful stuff here because we've got one function, copy, and it handles all of the copying that I want to do. All right, the next one is sort. That's just standard sort, and we're doing the same sort of thing here. It's going to sort some range of data. You see that if I give it a place to begin, it's clear in vector when I call vector.begin, and we see it's pretty clear where the beginning is when I give it a pointer, C-style, and is a little bit less clear as you look at this as R plus N, and that helps us as we think of our zero-based indexing. R, the array, plus N, the number of items in the array, is going to be looking at, basically, if I look at addresses, I might say, well, R is at index 0, and R plus N, 100, is at index 100. And that's great because I never want to square brackets 100 if I've got 100 things in there. I only want to square brackets up to, but not including 100. So this then says, I will go from R at index 0 all the way up to R at index 99, but I'll stop before I get to index 100. And this sorts them. This same call works again here on the vector, same function. It happens because we can use this generic programming. The last one is just another couple of cool things that you can see in the STL, different types of iterators. It's got an interesting name. It's reversed. This is not a function. This is a variable declaration. Pay close attention. This is a variable declaration. Type, vector of int, name of variable, reversed. That's it. Simple and straightforward. Vector of ints, named reverse, but we're also going to initialize that vector of ints, and you can do that by passing a range to a vector declaration. And what that does is it fills that vector at declaration time with a copy of everything within the range that you pass to it. So the range is two separate iterators, v.rbegin and v.rend. And what those are is reverse iterators. So a reverse iterator allows you to plus, but while you're plus-plussing, you're sort of moving from right to left. We think of plus as a move from left to right, and that's good. An R, or a reverse iterator, is going to allow you to plus and go in the opposite direction. And that is just another great way to do some generic programming. If you think about it, I might want to come up with algorithms that sort of do things in one direction. I say, well, what if I wanted to do them in the other direction? Two options are, I could rewrite the algorithm, right? So then I've got a copy of every algorithm that works forward and a copy of every algorithm that works backwards. Or I can create these reverse iterators And in the reverse iterator, I just stick it into the main algorithm, and now plus plus, instead of moving me forward, moves me backwards. So that's how you can think of this. So what reversed is now a new vector of ints that are all of the data in V just in reverse order. So we know that from line 15, V is completely sorted. So I can see them as being sorted from small to large. That's what sort means in general. Sort increasing, unless it's specified otherwise. Sort is always an increasing sort. So 15 is sorting V in increasing order, and then 16 makes a copy into another vector called reversed, and of course the values there are in reversed order, so they go from large to small, but sorted order, decreasing sorted order. This next slide of it, it's almost identical to the previous slide. The small difference here is since C++14, we've got these new function adapters here, and it's standard begin and standard end, right? Standard begin and standard end. And what they do is, if a container, for instance, I use standard begin on vector, like in line 12 here, begin of V, this is just going to pass that through to call v.begin. So there's no real difference in this one. However, before I was using just R, what begin is going to do for me is get me an iterator that's going to shadow this C style pointer, right? And because I am in scope where this thing is declared, right? This has to be done inside the scope that it's done in, right? I can actually call end on R. And what end on R is going to do is give me an end iterator equivalent to where the C style pointer R stops, right? And this is why it's important that it's done inside of the scope here, because I can't just pass in any C style pointer from anywhere to an end function and expect to be able to get the proper ending of that. You can see here that because R is declared inside of this scope, the compiler knows that R has a size n, and so it can, at this time, it can set up that distance properly. So you can't just write a function, for instance, that you pass a C-style pointer to, and that pointer comes from anywhere, and expect that function to be able to generate an end iterator. But this one makes the code a little bit more similar across the board. I can always use begin, end on whatever it is. I don't have to use the dot. It also saves me an entire character, which is very important. Sarcasm. But you can see that I'm going to spend those characters instead of using end R or begin R. I would just use R there. But this lets this whole thing sort of work inside of real iterators. That's what's going on there. Other than that, you see there's a standard R begin, standard R end. There's even more than that when I'm talking about getting these iterators. I've got different types of iterators. And so we're going to look at them. You've got a lab coming up that's going to help you deal more with them as well. They're similar to pointers. They can be copy constructed. They help us access these container members, right? Items in there. And we've got an input iterator. All of our iterators most of our iterators sort of have this concept of, I'm going to use an iterator to move through the entire collection. So I can use the iterator in sequential access methods. An input iterator is a broad class of iterator, so you don't actually declare an input iterator. You get an iterator that is responding to this input iterator type, where an input iterator is used to read from. You're trying to get input, you can read from an input iterator. And you can move forward with it. So after I've read some data, I can plus plus and read the next data item. Plus plus and read the next data item. The way that input iterators get constructed, however, you cannot do multiple passes. You can't just say, I'm going to go and reset this thing and input across it again. They can be incremented, they can be compared, and they can be dereferenced. Those are the things that I need to do reading. Incrementing says go get the next one. Compared means I can use this comparison to say, well, is this input iterator at the end? Because if I couldn't compare an input iterator to another iterator, I wouldn't be able to know when to stop. That's what the comparison is there for. So I need to be able to say, hey, is this iterator at the end? Because if it is, then there's no more data. It can be dereferenced. Obviously, if I couldn't dereference it, I wouldn't be able to read it either. Output iterators are similar in that they move forward. but I use them to write values. I can't use multiple passes there as well. They can be incremented and dereferenced, but they cannot be compared. So you can increment it to say, now I'm ready to write in the next position. And it can be dereferenced to say, write this value here now. So that's what the dereferencing and incrementing are. So you be careful on this one, because the comparison, as you saw when we did that copy function in the previous slide, copy had 3 parameters, 2 from the input and 1 from the output. Without the ability to figure out when I should stop writing, copy never tries to figure it out. Copy figures that you should know you're copying 15 items over, you need to have room for 15 items. I'm going to give you speed by not ever even checking to see if it's valid for me to write. You are supposed to figure out that I have enough memory, and if you do that, then I will give you the most possible speed in copy. So that's why there's 3 parameters, where to start and where to end on the input data, but just where to start on the output data. It's going to write all of the input to the output, no matter what. So you make sure you got enough room there. Don't shoot yourself in the foot. A forward iterator is a bit of a combination. So now I can read and write with forward movement. I can plus this thing, I can increment it, I can compare it, and I can dereference it, obviously. Now, the other thing that the forward iterator gives me is the ability to store the iterator's value. So one thing that you can do with the forward iterator that you can't do with an input iterator is you might be trucking along and say, hey, this is an interesting piece of data. I'm going to save a copy of this iterator location so that I can come back to it. You cannot do that with an input iterator, which makes sense in terms of how input iterators are often used. They're often used with streams. So as I'm reading things from a stream in a file or a keyboard input stream, you can't just pick a place to stop and hold this on for later. So you can't store those. Forward iterators, however, you can access the same value more than once. It said no multiple passes with input and output iterators. Forward iterators allow you to do that. A bidirectional iterator is the same as a forward iterator, but it also can be decremented. So it can be incremented, decremented, compared, and dereferenced. A random iterator is a bidirectional iterator, but you can do pointer arithmetic on it. So a random iterator would allow you to get square brackets access into things. So I can do pointer comparisons and pointer arithmetic. Reverse iterator is just an adapter that inherits either from random or bidirectional, and what happens in a reverse iterator is plus just moves from right to left. So it's got a sort of an overloaded plus that makes it look like it's a decrementer. Good reference on this in cppreference.com. Go check out iterators.html. They generalize pointers. That's what iterators do, and they're really helpful, as I've already mentioned, in allowing the same algorithm to work for multiple data structures. They're great. They support the sequential access, and they are actually faster than square brackets. So as we look at sort of this thing right here, I've got this C-style array access with an I++, right? Sort of comparing those to what if I had an iterator. Now, the way that you look at this is, here's where my data looks like. And R is always there. Whereas it is wherever I'm looking. So it ends up being slightly faster because as I dereference it is pointing at the data already. If I try to dereference R, I can sort of dereference the thing that R is pointing at. But if I wanted to dereference this location that it is pointing at with R, I'd have to say, well, let's take R plus 5, right? So there's some math in there, and then dereference that. So I would do an additional arithmetic operation there, an addition, to get to it if I was using R as the location. Whereas because it is an iterator and it's always pointing at the thing you want, then my increment here just means move this over one, and then as I've moved it over one, the next time I go to dereference it, I can dereference exactly that memory location, right? If I'm using some I here, every time I want to dereference R with those square brackets, I'm going to have to do this math and the dereference. So that's why iterators write faster code for traversals than your own for loops. Here's a generic, an additional addition. That's correct. Exactly. It's better than multiple multiplications. So, this generic print function, you see this one works with iterators. And this is great as long as I can pass something in that behaves like an iterator. It doesn't even actually have to be an iterator here. Just keep in mind that when I call something here with a template, this class name, or if you use type name in your iterator, your template declarations, either one of them works. Whatever this is not enforced by the compiler. It doesn't have to be an input iterator. We're just trying to let the people who use the code know this thing should behave like an input iterator. And I'm going to refer to it as input iterator for the rest of this code. So here I say I've got something of this type that's being passed in, right? And as long as this type can be compared, like in line 4, it can be incremented or dereferenced, like in line 5, this generic print function will work for anything. I can pass it iterators to a deck, iterators to a vector, C-style pointers. I can pass it a bunch of things and it's just going to work. So this is really nice. This is generic code. Iterator ranges, we talked about them already with .begin and .end, and with the newer stuff in the standard library, since C++ 14, I don't have to even use the dot. I can just use standard begin, like that. And I've got standard end, I've got standard cbegin, and what is that? That's a constant iterator, meaning that thing is going to give me an iterator to an object that can't be changed, right? I've got cn, which is the end of this in constant respect here. I've got rbegin, which we've already looked at in rend, and there's one more, is rcbegin, which is a reverse constant iterator. But there's a bunch of different ways that we can get these ranges, right? And we see here cbegin, standard begin, standard end. Those things are all added for C-style arrays. STL, remember I talked about this only operates on iterator ranges. It doesn't work on containers. They don't have algorithms for decks. They have algorithms for ranges, and you can get a range in a deck. You get faster traversal with them. You can try it. It's a real simple one to try. Try to, for instance, just fill a large array. Declare an array of size 100,000 and fill it with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just fill it with something like that with your own for loop, and then try the same thing with a function from numeric called Iota, which fills something with 0, 1, 2, 3, 4, 5, and so on. So you can use Iota, which is going to be using iterators as an STL function, versus trying to write your own for loop, and you'll see a real simple speed difference there. So try to use the STL and try to use iterators whenever possible. If you want speed, figure out how to do it. There's things that can be applied, map, reduce, for each. You can do all kind of really cool things that in classic programming we would just write a for loop to do. For loops and functors, you can really make a lot of things happen. So this is an example of when we can't use iterators, right? So if you try to write some templated version of a function that doesn't use iterators, right? So, well, I can write my own sort of generic output stream thing. All I have to do is template on the container, and I'll pass in whatever container I want there, right? And here you see that the template is on the container. So the author is maybe thinking, well, sometimes I'll call this with vectors, sometimes I'll call this with decks. It'll be great. Then I won't have to write multiple ones, and I only have to deal with begin and end. I jump inside there and say c.begin. This ends up as being ambiguous because different objects may or may not have or implement .begin the same way. So the compiler can't call those things in that way. So this version here would not compile. Same thing here is just another version of it trying to template on the container and not on the data. And we're using an auto, right? An auto as well as a range-based for loop. Neither one of those are going to compile because it ends up being ambiguous to the compiler because you're trying to template over the container. So the way that you really need to do this is template over the data type, right? So here you see we're templating over some type t, and then the function takes a vector of t's. So then when it comes time for the compiler to say, how do I range-based for loop over a thing, it knows what that thing is. That thing is always a vector. It is always a vector. It's a vector of t's, which the t is unimportant, but we know that this is going to work. In the end, x is going to be auto, and since it knows that x is a thing inside a vector of t's, the type of x is going to be t, a reference to t. And so in this case, we can see out that. So this code compiles, no ambiguities. Of course, you've sort of been limited. You're like, well, now I can't do this with dex. If you wanted to do this with dex, you're going to have to write another version for dex. If you want to do this for list, you're going to have to write another version for list. And the STL is avoiding this because it doesn't try to stick containers in there. It tries to stick ranges in there. So, it's pretty bad. Don't try to do it. Do things the STL way. There's a reason why the STL does it. It does it that way for a reason. Initializing elements of a container. How do we get stuff initialized? Be aware that this is a great slide for you to get things set up in P1. But there's only so many slides that we can get in front of you before P1. But C down here at the bottom is a great way to declare a two-dimensional array. All right, you see I've got a size here. This is the number of rows. And then here I've got a number of values in each row, or the column width, right? So I can see this is a vector of ints that has 10 vectors. Each one of those vectors is holding 20 ints, and they're all initialized to -1. So that's really a straightforward way to do this. I can't express how important this is to understand this. I see people in the last semester, as we graded the final exam, when they're writing code and they're trying to initialize a two-dimensional vector, they're written their own loop, like here, to say, well, I'm just going to make one, and then I'll resize the outer one, and I'll go through and I'll resize the inner ones, and it's just a waste of time. It's just a waste of time in coding and execution. So try to get this under your belt here. Simplify this for one-dimensional. You can do it here for two-dimensional. Make sure you can take it up. Do you understand how I might do this for a three-dimensional vector? How can I do this as a one-line declaration if I know all three of the parameters for x, y, and z? Can I declare a three-dimensional vector in one line and fill it with the default value? You should be able to do that, right? We talk about these data structures here. We think of the vector as being very compact. It's got a memory overhead that's minimal. It's constant. It's 24 bytes every time. You've got a base pointer, a capacity pointer, and a size pointer. The rest is all data. The list, in terms of its memory overhead, is a doubly linked list. So it's got a forward pointer or a next pointer and a previous pointer for every object. So for every piece of data, there's an additional 16 bytes of memory used. So that gets to be quite large. And then as we look at the unordered map, that's something we can use later. The unordered map is really quite a memory hog. And we'll look into the unordered map because the unordered map is a hash table, and we're going to spend a real decent amount of time in hash tables in the second half. And we'll see why it uses so much more memory. But that memory is done in the standard sort of trade. I'm going to use a lot of memory so that I can get speed. And you're normally willing to pay that price. I'll pay the memory price to get speed if I can. If I can't afford the memory price, then I just have to go a little bit slower. I talked about this, the standard vectors overhead. I've got 3 pointers: begin, capacity, and size, right? Here's begin, here's capacity, the end of the allocated memory, and lastly, the size, the end of the used memory. Used as in used for data. So this is how pushback works. Pushback continues to move size until it hits capacity, then it gets more capacity, and you can keep pushing back. Be aware that vectors have this constant amount of memory involved with them, these 24 bytes per vector. So if you end up with a lot of small vectors, you end up with a lot of extra memory. I've seen people try to do things like in project 1, as opposed to using a struct, they would just a struct for XY location. They would try to say, well, I'll just push a vector of size 2 into this deck. And it's just a tremendous waste of memory. You got 4 bytes of data for an X coordinate, 4 bytes of data for a Y coordinate, and 24 bytes of pointers for every single coordinate that you're putting in there. So you take something that should be 8 bytes per, and it ends up being 32 bytes per, and that's just terrible. So be aware that that's the thing that you want to be avoiding. Try not to use a bunch of small vectors. And if you have to do something with a lot of vectors, like a 3-dimensional vector, remember a 3-dimensional vector is a vector that has a bunch of vectors in it, and each one of those vectors has a bunch of vectors in it as well. So the ordering of this is important. When we talked about earlier skills of the programmer here, you can see that this declaration of this 3-dimensional array, R3D, has A, B, and C as its sizes, right? So the overhead in terms of pointers is my outer vector has 3 pointers, because that's where the outer vector begins, ends allocation, and ends memory used, right? Inside that is a bunch of vectors. There's A vectors inside there. So there's 3 pointers for each one of those A vectors. And inside each one of those A vectors, there's B more vectors to give me this 3-dimensional thing. So I'll end up with 3 pointers for the outer, 3 A pointers, a set of pointers for each one of my inner vectors. And then because there's vectors inside of each one of those, I'll end up with 3 times AB more pointers. So I can reduce my memory overhead just by putting them in a good order, right? So I want to put them in increasing order here. A is less than B is less than C as I declare that. And a real concrete example of how I might do this is, what if I had to store 10 million items in a vector that was 10 by a million, right? I could sort of do it horizontally and have a bunch of vectors in here, or I could do it vertically and have sort of just like 10 vectors in here, right? So if I was doing this, I might say this is 10 by 1 million. Or this is 10 here by 1 million, right? So in this case, I end up with 1 vector on the outside and a million vectors on the inside, which ends up being how many bytes? Well, for each one of the million vectors, I need 24 bytes. So there's 24 million bytes plus 24 bytes for the outer vector. So this version of it would be 24, this many bytes just in vector overhead. Now this version, since it has 1 on the outside and 10 on the inside, I end up with how many bytes involved, right? The 10 inner vectors, all of width a million. There's a million pieces of data in there, but each one of those vectors only holds 24 bytes of overhead. So we got 240 bytes for the inside and 24 for the outside. I end up with 264 bytes for this version and 24 million for that version. So same amount of data, vastly different amount of overhead just because of the order that I declared them in. Utilities and function objects, swap and max, they're things to understand and know. See the STL for more stuff on utilities. That's another really good library to understand and be familiar with, just so you can call things out of it. Function objects, which we'll be using plenty, have a bunch of different names. So they're officially called function objects. Then they get a nice name called functors, which is a short version of function objects. Then we have a particular name that we also apply to function objects, or functors, that take 2 arguments and compare them and return a bool. We call those comparators. A comparator is a function object, a comparator is a functor, but it's got a particular signature. We're looking for 2 things of the same type or similar type, and then they come in and return a true or false to tell you whether they're in the right order or not. And then another one that we also use is a function object or functor called a predicate. And all that is a single parameter function object. And it's going to return true or false to meet whether or not that object meets some criteria. So that's kind of some of the language that we use around function objects. Also, since C++11, there's lambdas, which we can use instead of functors. A functor is something I'm going to write separately, whereas a lambda is an anonymous function that I can write inline. I can even write a lambda in a function call itself. So the definition of a lambda often cases happens right inside of the function that's using the functor. So we don't cover them in 281, but if you go look at some code on Top Coder, you're going to see a lot of people using lambdas because they're so powerful and quick, and you can use them to take the STL library functions to new levels really, really quickly. Using a functor, here's an example of one. Suppose we want to take some class employee and have a collection of them and sort them. One way to do it is I could just overload operator less than, because then standard sort, could look at two employees and say, well, is this one less than that one? Because if so, then I'm going to put the smaller one to the left and the large one to the right, and that's how I sort things. That's all that sort does. The problem is if I overload operator less than, it sort of locks me into being able to sort this in one way and one way only, right? So you might say, well, I've overloaded operator less than so that I can sort these things in sort of increasing order by last name, comma, first name. That's great if I only ever want to sort things that way. But what happens then if later I would like to say, well, I need to do this for payroll. I need to sort them in terms of salary, or I need to do this for HR. I need to sort them in terms of seniority. With operator less than overloaded for only name-based sorts, I still have to write a functor to do any of the other sorts. So the best way to do it is to always just write a function object, some functor that helps you do some sorting. And in this case, what we're going to do is we're going to create some object. What is the object made from? Doesn't matter. It can be a struct, it can be a class. We've already talked about those things both generate the exact same executable code. So it can be a struct, it can be a class, it's up to you. But what it does have to do, this object has to have this exposed overloaded operator parentheses, right? In this case, we're writing a functor that is a comparator, so it's going to take two objects and return a bool. But the function has to be operator parentheses, and it has to be exposed as public. So here, inside of a struct, of course the function is public. If I put this inside of a class, I have to make sure that the operator parentheses is declared after the public declarator. So be aware of that. Now, what else is going on in here? I'm going to pass in these two object references, left and right. I'm going to pass them by reference because that's faster than passing copies. I'm going to pass them as consts because this is a comparison. I don't expect a comparison to modify those values at all. So I'm going to pass them in as const. It allows the compiler and the execution to speed things up as much as possible, if possible. It certainly never goes any slower. So I'm going to pass in two values and return a bool. And all that is saying is the thing on the left compared to the thing on the right, are they in the right order? If I looked at them in a lineup, this thing on the left, should it be to the left of the thing on the right? And if you say true, sort behaves appropriately. So there's one more const here. Don't want to leave that out. What this const is saying is this function, operator parentheses, when it's called, it will not modify my sort by name object. So this const says nothing here will be modified in this object, which is pretty hard to modify that object. There's nothing even in the object. There's no members or anything. But when the compiler knows that the object won't be modified, once again, more speed can happen. So the STL loves to work with less. When you look at how sort works, it can sort things as long as it can figure out if the item on the left is less than the item on the right. That's why you do have the option to overload operator less than. But we're saying a better way to do that is to provide a functor that behaves like less. Because what happens is when you call sort without a functor, it uses a function called standard less, which can be applied to any built-in type, and it can just answer the question, is 4 less than 6? True. Is 10 less than 14? True. Is 15 less than 4? False. That's all you're doing as you're looking at these things coming in. Is the thing on the left less than the thing on the right? In a comparator, I just want to say if the thing on the left is less than the thing on the right, return true. Here's another example using functors. It's called index sorting. And in index sorting, what we're going to do is leave the data in its own original order. But we're also going to have a list of indices that allow me to access the data in sorted order. So my input here might look something like, let me draw up some input here. My input data might look like a 3.1, 0.2, 1.4, 5.9, right? Now let's make that a 2.9. 2.4, 1.9. There we go. I like that order better. So there's my input data. Now, if I want these data sorted, we can see that the first thing should be 0.2, followed by 1.9, followed by 2.4, followed by 3.1. With an index sorting, what I want to do is, come back, hold still. All right. My index sorting, I'm going to end up with something that looks like 1, 3, 2, 0, right? And so index sorting is indirect sorting because I haven't sorted the data, I've just sorted their indices. So if I want to find the first or the smallest item, instead of looking into my data, I look into my index. I say the smallest item is really at index 1. So I take this 1 and square brackets on the data at 1, and I find that gets me 0.2. Where's the next item? I go to index 3, so that's square brackets here, and I get 1.9. I go to index 2 to get the next one, that's 2.4. And finally, I go to index 0 to get the last one. That's what index sorting does. It's the act of setting up these data to properly order these data there. And I'm going to do this with a function object. And this one is called sort by coord. We're sorting this thing by coordinates, and it, of course, has a public operator parentheses. And that public operator parentheses takes in a couple of ints and returns true. In this case, I'm not going to pass in const reference to ints. That's a bad idea, right? If I'm just using these things in comparison, I can pass in copies. There's a copy of I and J, and using the copy of the int is smaller and faster, right? A reference is really like a pointer, so if I'm passing in 2 references to integers, now instead of passing in 2 4-byte things, I'm passing in 2 8-byte things. And since they're like pointers, they also have to be dereferenced to get their values. So in this case, as I pass in copies, the compiler knows that passed in as copies, they won't be changed, so I don't need to make them const. They're smaller and faster, and in this case, better. So knowing when to use const and when to use reference is a tool, so get after it. So in this case, now what I'm saying is I and J, these ints, are going to be members of this index array. So they are not going to be my data, they're going to be the address of my data in a sense, right? So you can see that my comparison that happens here in line 8 is not comparing I to J, it's comparing what's at I to what's at J, right? And this coords reference is just a direct reference to my input data. That's what it's there for. So you can see this class has a constant reference to a vector of doubles. I'm going to use that and call it coords. I've got a constructor in line 5 that assigns the value to it. So you have to create one of these ahead of time by passing in a reference to the data that is going to be index sorted. Then whenever the STL function that needs to know something about a pair of items says, well, what about this index and this index? The instance you have of sort by coord has its own reference to the data. And so as the 2 indices gets passed in, sort by coord can say, well, I'll go look those data up and tell you whether or not the first one is less than the second one. So the body of our code that happens down below, I've got this vector of unsigned ints. This is going to be my index vector. And I've got this other vector of coordinates. That's going to be my data vector. This for loop, all it does is fill the indices from 0 up to 99, n minus 1. Fills the indices up there in order. And then it also fills my coordinates with something that's random. Just gives me a random number and turns it into a floating point value. And so now I've got some random stuff in Xcoord. And in the end, I want it to stay in that order. I might not have access to change it. It might be too expensive to change it. If I've got big memory items, I don't want to move them around. Might not be my memory to sort. So, or I might need it in the original order as well as this supplemental order. So this is the reason why we use index sorting. Sort by coord here. This is a variable declaration. I'm declaring an object of type sort by coord. Its name is SBX because I'm going to be sorting by the X coordinate. And then I have to pass in a vector, a reference to a vector of doubles. That's what the constructor here in line 5 is requesting. So SBX at X coord gives me this functional object. So now I can use SBX anywhere a functor would be applicable. And I'm going to do this by using sort. Sort from begin to end of my actual data. Not my actual data. Sort from begin to end of my index because I'm changing the order of the index array so that their values are the sorted order of the indices of the original data. So I've got the two parameters that I did in my first version on the previous slide, just using sort. When sort knows how to sort things, if it's got a natural ordering, sort of a built-in type, I don't need to add a third parameter. But in this case, since I want to do something special, I'm going to pass in this third parameter. And that's what sort uses to sort of compare things, break ties, and so on. So this one, when you run it, it'll put things from some input like this into some output like that. You saw me fill that index vector inside of my for loop. And if I wasn't already writing a for loop to do this, I would probably just use Iota. But since I already had a for loop cooked up and running, I just assigned values into index as I was going along. But if I was just trying to fill one without other things going on, I would use Iota because it's faster. You can see that in numeric and Iota from beginning of the vector to the end of the vector starting at 0. So the first thing at begin gets 0, then 1, then 2, then 3, then 4, then 5. If you wanted to change what that began at, you could say, well, I want to start at 1, so I can go 1, 2, 3, 4, 5. That's what Iota does. Look it up, learn it. It's a good thing. Here's a great way to do some testing. This is a way to generate random permutations, and you can see some good code here. If it doesn't make a whole lot of sense, then spend some time reading it. We've included some libraries, IOStream, vector, algorithm, numeric, and random. And we run through and create a random device, which is something that you can get out of the random library. The random device then creates is used to create a Mersenne twister, which is a particular type of pseudo-random generator here. That's what this type is. So the type is MT19937, which is a Mersenne twister that lives up to a particular specification, this 19937 specification. So what that does is it just generates something that does a really good pseudo-random generator. It's not fast, but it's very good. All right, so Iota is then used to fill the data in values from 0 up to, 0 up to 19, and shuffle puts them into some new order. That's all this does. So this is great. This is a great way to do testing. You don't want to try to test a lot of times with just purely random data. When you're testing with purely random data, it's hard to know what the correct answer is. So this is a good example of a way that I would do this is instead of having purely random data, I might say, I know exactly what the data is, and what I'm randomizing is the order. So this might be good for testing in your project too when you're trying to figure out how do I get a running median. I don't know if my running median calculation works if I just pass it a bunch of random numbers because I don't know what the median is. If I just pass it random numbers. However, if I take a fixed set of data, the values from 1 to 100, I can calculate that median ahead of time. And then if I scramble the order of those things, I should be able to figure out no matter what the order is, it's always, because it's the same data, it's going to have the same median. So this is a really smart way to do things. You can use this for generating test inputs for your program and so on. So that's all that's there. Debugging STL heavy code, we've got compiler errors. Oftentimes the compiler is going to complain about headers, not your code. We call these induced errors. The error has never, in my experience in 281, been in the STL. Students' code has caused the error, this induced errors, because something that they've written poorly in their code finally gets percolated through and then shows an error up in the STL. The error, though, is not in the STL. It's in the student code. Oftentimes, this is just about checking function signatures, passing in the wrong types. This is almost always the thing to do there. So make sure as you read those errors, they're really hard to read because they're usually, 140 characters long, and they wrap around, sometimes longer than that, because it's a whole bunch of type information. So it's like parameter 1 of type this, type, comma, expected to be this, not receive that, type. So really all it is learning how to break those things down and shorten what you're looking at. It's generally saying, you know what, you passed in a pointer to this thing, and I didn't know how to deal with that because I was expecting not a pointer to an object, but the object itself. So double check your function signatures, and you should be able to figure out how to get rid of some of those compiler errors. Most of them, I would say. What about runtime debugging? Crashes can also occur inside the STL code as well, but same thing. I've never seen an STL error in 281. It's still something that's been done in student code. So you can check this out when you're debugging if you use some way to investigate your call stack. In GDB, you would use where or backtrace, the BT command. I know that in the runtime section on the left-hand side of Xcode, when you're in debug mode, you can see the call stack, and that is somewhere near the center top on Visual Studio. But you can always look at your stack frames and see where does this happen, right? And oftentimes you'll be 3, 4, 5, 6, 7 different levels deep into the STL making calls when the crash occurs. But if you back out of those stack frames till you get to the last piece of code that was yours, that's where the problem happens. This next set of slides is just a bunch of comparisons. These are empirical comparisons of the STL containers. And so this is a great way to answer questions that I get a lot of times in class or in office hours and say, well, which one of these should I use? Should I use the vector or should I use the deck? Well, what are you doing? It depends. It's 281. It depends. Should I use this or that? Well, it depends. What are you going to do with it? So this is a bunch of pictures here. We can see they're graphs. And what happens is we've got some testing that's gone on over here, and this explains what the test is. Then inside the graph, we see some time here. This is how long time took. And then this is the data size along the bottom. And then the different colored lines show you which container was used to do that. So this first example is fill an empty container with different values. That's it, right? And it talks about vector pre was just a vector that was used to be, it was resized ahead of time. So there wasn't the vector push back and grow used in there. So all they did was take these containers and fill them with 100,000, 200,000, 300,000, all the way up to 1 million items and sort of graph that in time. And you can see how vector and deck and a pre-sized vector are all pretty similar. They're very close. Why should they be that close? Well, a deck doesn't have to do any sort of reallocation. The vectors have to do reallocation, but then because they keep their memory contiguous, remember decks aren't contiguous. They're chunks of contiguity, but they're not all contiguous. The vector ending up being completely contiguous ends up being faster. The pre-size vector, we knew what size it was ahead of time and resized it first, and then sucks things in there. So there's only one memory allocation. Ends up being slightly faster as well. Not always that much faster. So it's great when we can do it, but if we can't, we're not usually getting speed out of it. What we're doing when we resize vectors ahead of time is we're saving memory more often than not, right? And you can see here that they're all much better than the list. They're all linear. As the data gets bigger, the time gets bigger. But the constant factor that's multiplying our linearity here is much higher in the list than the other containers. And that's because if I've got a million new adds into a list, I've got a million different allocations, and that's just a slower operation. So each one of these shows a different behavior. Here, we're going to fill the container with a bunch of numbers, shuffle them at random, and then search for each value using find. And you can see how deck, list, and vector behave with these things. There's no reason to pre-size now, so we're just going to use deck, list, and vector. You can see that when I'm doing a find on random data, it's fastest in a vector, slowest in a linked list. How about insertion? So we take some numbers, shuffle it at random, pick a position, go to that location, and insert 1,000 values. Almost constant with the list, because it's just about finding where to get things going. Once you've got that found, the insertion is constant time in terms of not having to move any additional data. The deck is faster than the vector because of the deck's two-ended nature. We know that if we insert something near the front of the deck, it pushes data in the front forward. If you put something near the end of the deck, it pushes data in the back backward. In the end, the deck moves as little data as possible. This is why it's generally faster for insertions than it is for a vector. This one is not insertions, it's removals. Go to that location, remove 1,000 elements. We can see a similar time profile there with the insertions and the removals. All of them show that sort of cutting out or inserting into a linked list is far superior in time to doing so with contiguous memory. But doing things with a deck ends up faster when we're pushing things around because of the two-endedness of it. Here, insert new values at the front. We're always going to be going at the front, and we can see how, because we're doing it at the front of a deck, the deck and the list here are so close on top of each other that you can't even see the blue line of the deck. That's what's going on there. You wonder why deck is missing. It's not missing, it's just being covered by list. It's a constant amount of time. There's no change when I'm inserting at the beginning of 100,000 items than there was when I was inserting at the beginning of 50,000 items, because I just allocate the memory in the front of the deck and insert it there. It's just like a list, except I do it in sort of one large allocation. Here is why we don't use vectors for everything. Sometimes vector is slower. We see vector winning in some things, so use charts like this to understand. Use sample code that you write yourself to get a good feeling for when I want to know this question, should I use A or should I use B? And the answer is it depends. What does it depend upon and why? What am I going to be doing? Am I going to be doing a lot of insertions? Am I going to be doing a lot of removals? Am I going to be inserting anywhere? Or am I going to be inserting at the beginning? I'm going to try to find something. Is it sorted? Is it unsorted? All of those things go into your consideration as you do this. So here we are, wrapping it up. We're looking at learning the STL. How do I do this? That was the goal of this lecture, talking about the STL. Your main reference is the Jasudis books online. You can use cppreference.com, c++.com. Read documentation. Just read docs. That's what you have to do. Read docs. Just like the student here walking through the library, just kind of looking at books. Find out where things are. You don't need to know the content of every book in the library, but if you need to know how to find a reference manual or science and nature books, if you're on the wrong floor, you're never going to get the book, right? So know what's going on in the library. Know what's going on in the STL, what the parts of it are, where to find things that would be interesting to what you're doing is, and then go look them up. If you need help, you can always ask us. Show your staff members, TAs, or professors. Ask for comments on your coding style, and we can help you with stuff. And familiarize yourself with the library. That's going to get you there fastest. Have a good day.